Hold on, Akmal. About flag control, I don't understand how the Boolean check false when user enter the number. Let me copy the program. Not in this machine. Akmal, is it a while loop or for loop? Or is it do while? Can't remember which one. I may not be able to find the exact match. But Akmal, can you tell me what is the number of the program code that I put there? Is it 5.3 or is it 5. I can't find it here. So maybe yeah.
Part 2.
Oh, part 2.
Ah.
Not the include. I think I didn't save the program. Can you share your screen? Show me the program.
Format data.
Okay. I think I didn't save the program because I can't find it here. Continue. It's Boolean, right? It's the print out 0 and 1, isn't it?
Program demonstrate checking if the number is under 25 using while loop.
Right. Okay. This program, yeah?
Yes.
Okay. You don't understand the Boolean is equal to false, but then here I said, what was the question again? Boolean check false when user enter the number. Okay, here is when user enter number here, you mean? Why the Boolean is why this statement is true?
Yes.
Okay, because here the flag that you use here is called found, but the number we key in here is variable number. So there are two different variable. When we are doing the while checking, why the number is here? Okay, let's move for this one further. So while not found basically means if found is equal to false. But of course, if found is originally initialized as false, only after this statement is executed, then found will be declared as true. So the C in here is number, is a different variable than the one that is checking in while loop. Did I answer your question?
When user input number,
Uh-huh.
y is how the y check the number instead of found.
The while didn't check the number. While only check the flag.
And the flag is if the user input number is just is determined found or not found. How it's determined?
Oh, they cannot determine from the first, because when the program goes in sequence, when they found boolean equal to false, they will remember found is false, and then we say enter a value. When the user enter the number, it is assigned to the variable number. But when they go into the while loop, they are not checking the number, they are just checking the flag.
Checking the flag is not found, it means true, okay?
If not found, go ahead. Okay. If here this statement is not found, basically it says while not found is while found equal to 0. This is what I mean. This statement, while not found, is similar to this statement, found equal to 0, because this is the negation of found. The exclamation mark is the meaning is not. So found, by default, we are saying something as true. But when we say not, so we are negating the answer. So this statement have no relation with this. In fact, if you see in something like, basically if you see in number, they will just go in here. If you see in something else, the program will crash.
Okay. Wait, doctor. Boolean found equal to false means it's true, eh? It's why?
It's false. This one is 0. Basically, boolean found is equal to, let's say you declare boolean found equal 0. This is a string statement.
If not found,
oh, you are thinking. All right, okay. Don't think in terms of your logic. Okay, because this one is this is an assignment. You assign 1 or 0. This one is an expression. You are checking the value 1 or 0. So basically here they said what is currently found is holding. Found is holding 0. So found is currently false. Because found is false, then it is not found. Okay. Now I get where the confusion come in. So if this confuse you, then don't use this. Just say found equal to 0, or you can also say found equal to false. I think we have to put, I think false is a keyword. Yeah, false is a keyword. So do like this instead.
Okay.
Okay. Yeah, it's understandable, right? After you explain it, then I understand what's the confusion.
Okay. Thank you, doctor.
Okay, welcome. So the increment and decrement after execute it, why the initial value will be stored as the new value? Hold on. For the increment or decrement, after I execute it, why the initial value will be stored as the new value? So you help. I don't get the question lah.
This is because I mean like when you insert the increment or the decrement, right? And then the slide wait let me show the slide.
Okay. Hi.
I understand about the logic of the increment and decrement. I just want to ask that why like after I put like num plus plus, right, and then the initial value I already assigned is 4, but after I assign this increment, then the number will be stored at 5.
Yeah, that's true.
But why like it will change into a new value? I know that it's plus 1, but why is keep continuously like change the constant that I have initialized at the first step?
Okay, you are referring to this program compared to the next program after this, isn't it?
Yes.
Why this one is they increment like normally, but the other one is they didn't increment like normal? Is that your question?
No, I just wonder why like this after I use these things and then the initial value that I already assigned will change to a constant. Like for example, the initial is integer number I set is 4, and then after I put the num plus plus, right, or plus plus num, the initial value, the 4 will change to 5, right?
Yes.
And then after I put another increment or decrement, they will use 5 instead of 4.
Oh yeah, because it's already assigned. That's why if you move forward to the video, you will notice that the is equal the equation is I plus plus or plus plus I is actually a different way of writing I equal to I plus 1. Except that for I plus plus is actually they have an addition of another variable. That's when I say I call j equal to I, and then after that I plus plus I equal to I plus 1. It's a what we call it's a shortcut operator basically. So when we use plus plus, let's say we have I plus equal 1. Okay. This one is equal to I plus 1, isn't it? Okay. This I plus plus or plus plus I is a more compressed way of expressing the same arithmetic operation.
Okay.
Yeah, it's just the value that is assigned. They keep it in that variable.
So it is normal to say that it keep it the value inside the after I use the plus plus or minus minus lah.
Yes. Unless if you didn't. Oh no. I'm sorry. Yes. Everything is kept. Everything is updated.
So that is the things that already set for this
C++
and minus minus thing.
Yeah.
Okay.
All right.
Thank you, Doctor.
All right.
Hello, Assalamualaikum, ma'am. This is Ridwan.
Yes.
Can I ask you a question about tomorrow's assignment?
Yes.
Ma'am, so it will be covered until week 4, right?
It will be up until week 4. Yes.
Okay, ma'am. And also, like, do we need to just write the course in Depth C++ and submit it in the e-learning allotted pages, right?
Yes.
The question. Okay. And ma'am, lastly, is it going to be the same question for everyone, or like it will be divided among the groups?
It will be very similar, but it's not the same.
So we all will do the same kind of, right?
Everyone will have the same evaluation, but there is a very minor changes for everyone.
Okay, ma'am. Okay, ma'am, because I was thinking about you mentioned about something the plagiarism, right? So if it will be the same for everyone, so almost like many of the answers would be the same, right? So that's why I was confused. Like, so
Don't worry, because if you write the program yourself, there are a
yes,
lot
ma'am.
of things that is not going to be the same. So
Yes, ma'am. Comments and many other things. Yes, ma'am. So okay, thank you, ma'am. Okay, take care then.
Shadow, it will not cover. It will only cover up until selection. It will cover up until switch. Okay. Jackson, for the first part, as I mentioned before, I cannot find a very stable, very reliable tools to draw in real time. So for the first part, we are not having any flowchart, and there won't be any pseudocode as well. Okay. There could be 3. If I can find a comparable question. That's the thing. When the question is not exactly the same, I have to make sure everyone is having the same standard of question. Okay. Yes.
Assalamualaikum and good day to everyone. We are
It's
now in
important to
week
have a
5.
comparable question.
We will go to the second part of control structure, which is repetition. Repetition is also known as looping control. So we are looking at the C++ repetition control structure system. So there are 3 ways on how we can do repetition or looping control structure in C++.
Yes. We'll have it at 10 until 12. Just make sure the slot is empty. I know not many have watched the while loop, the for loop yet. So it's okay if you want to watch the video now. But in meantime, if you have any question, just ask. Eighteen point five and 25 are included in optimal weight. Eh? Hold on. BMI is between 18.5 and 25. If BMI is less than 18.5, the person is considered to be underweight. If the BMI value is greater than 25, the person is considered to be overweight. 18.5 and 25 are included in optimal weight. Yeah lah, should be right. Okay, this is your lab question, is it? Hold on. The question is not here. Hold on, Legend. The variable initialized inside the loop considered as a local scope. Yeah, let me check the question again. I forgot what happened last week.
While loop, there is also for loop, and the other one is do while loop. The
What
name
number is
refers to the
BMI?
keyword that we're going
5.
to use to construct the looping structure. However, before we start with constructing the looping or repetition structure, we have to know first about increment and decrement operator for prefix and postfix notation. What do I mean with that? Increment and decrement operator is a special symbol that is used to increment and decrement a number. So these two symbols, it's not written as a mistake. We have to use double plus for increment and double minus for decrement. There are two types, prefix and postfix. We use an example that most of us familiar with already, I equal to I plus 1. Whatever value I is holding, they will increment by 1, and that value will be assigned to I. If we write using increment operator, prefix method, this can be written as plus plus I. If we are writing this in postfix, it will be I plus plus. Is there any difference between this statement and this statement and this statement? Theoretically, no. But this statement and this statement will produce a slightly different result in your program. We will go to that later. The same is applied for the decrement value. So if, let's say, you have j for the decrement value. So if, let's say, you have j equal to j minus 1, then we can rewrite this in prefix notation. Sorry, minus minus j, or postfix notation j minus minus. How do they differ? Let's look at a program. Look at how the increment and decrement operator are used in a normal program. I highlighted the variable affected. We declare an integer variable called num, line 7, line 14, num plus plus, and then we see out 8. So these 4 should increment by 1. When they print it out, it should print out as 5. And if we print increment again using prefix notation, it will become 6. So let's say So the first value is 4. We printed here 4. The 5 is the one I highlighted, line 14. This is line 19. So it becoming six. Then we do the decrement. Line 24, num minus minus using postfix. 6 minus 1 is 5, and then minus minus 1 is 4. From this is what I mean when I say theoretically they will produce, they are the same notation with the same meaning, but they have a slight difference actually. Looks about the same, and they will produce they are the same notation with the same meaning, but they have a slight difference actually. Looks about the same except that we didn't do any assignment process. We just see out it just to see how the value changes throughout the program. So let's compile this. So we have an initialization, integer number 4, num is 4, and then we see out the first value, line 10 it is 4, and then num plus plus, but the answer is still 4 when we see out it. But here on line 12, we see when we print out num, it becoming 5. Okay. However, for prefix increment, we understand line 24, practically the they will add the let's compile this. So we have an initialization, integer number 4, num is 4, and then we see out the first value, line 10 it is 4, and then num plus plus, but the answer is still 4 when we see out it. But here on line 12, we see when we print out num, it becoming 5. Okay. However, for prefix increment, plus plus num, the value change straight away, 6. So the same case happened for the decrement. So here the value of num is equal to 6 up until line 14, but on line 16, okay, sorry, 16 still print out the current value, 17 num minus minus, postfix. We know 6 minus 1 is 5, but the answer is still 6. However, in the next line, it's suddenly becoming 5. But you cannot say these two are similar because this is 5. By right, when we print out this should be 5 as well, but it's not. When we use prefix, the effect is taken straight away. The effects happen straight away. So what can we conclude about the two operators, the two mode of the increment operators. For postfix, when they have a cout instruction like this, they will give out the value first before they evaluate the value. That's why when they print out, the value here is similar to the value line 10. However, when the lines end, the increment process already happened. That's why in line 12, the value is incremented. For prefix notation in line 13 here, before they cout, they have to evaluate the value first because they found the operator first. So the increment need to be done first before cout can produce the answer. That's why the increment happens straight away when we are doing prefix notation. So if I want to conclude the difference between the two, I can write something like this. What's the size of it? Okay, so num is equal to 4. Line 10, just display it. Line 11, display the 4. Then adds 1 to num. This is what I mean. They have to print this one out first before they evaluate, before they do the increment. When they reach the end of the line, this value already incremented. That's why it can display 5. For prefix, add 1 to the number first, then display. So these are the very subtle difference for prefix and postfix notation or mode of the increment and decrement operators. So if we are to conclude the difference between the two, we can rewrite the program in slightly different way like this. It's not saying that the program can be rewritten like this, but in short, if we are doing plus plus I or the prefix notation, we are declaring, we don't waste a space. The same variable I use are calculated and then returned back to the one that is incrementing it for prefix. But for postfix, it's like we are declaring a new variable to assign the previous value to hold it temporarily, and then we increment it just because we want to return the previous value rather than the new value. So if you are asking prefix is better than postfix, or is it should you just use prefix rather than postfix? Uh, it's not exactly the point because the operators are given for you to use inside C++ programming, but you have to understand the caveat between the two in order to have the whole control of your program. About looping increment and decrement operator. Now let's go back to our looping control structure. We're going to use the increment and decrement operator quite extensively in this particular control structure, and you may almost absent-mindedly use it after this because that is how the control structure can be controlled, at least for one of the approach. I think I'm going to stop the video here and we'll do another video just for the control structure. See you in the next video. Hi, welcome back. Let's look at the subtopic.
Assalamualaikum warahmatullahi wabarakatuh and good day everyone. So this is the pre-recorded video of Monday class for 9 November. November 2020 for CPT 112 class. Okay. For this class, I would like to continue to discuss on a few questions taken from tutorial 3. So let's start with question 9 because we already discussed on question 7, A, B, C, D, E, F and question 8 in the previous recorded video. So here, I will just continue with question 9. So what's the question? Determine whether each of the functions 2 power of 2 plus 1 and 2 power of 2 plus n 2n is the big O of function 2 power of n. So please be aware of the question. It has 2 questions here. So first you need to settle this one. And the second one, you settle this, okay? 2 problems that you need to solve. First, we solve the first function first. So the question asks you to determine whether each of the function is the big O of 2 power of n. So none. Now, for the first one, because of the x, it use n, so we just simply replace x with fn. Doesn't matter. So this one is modulus of fn. As for big O is less than or equal to c g n, and the fn just replace with the function 2n plus 1 less than or equal to c 2n. Okay. And then this one is equal to 2, and we would like to just simplify it just to get similar to 2 power of n. Here 2 power of n is equal to 2 power of n times 2. This one is actually 2 power of 1. Okay. And just rewrite it again. Don't be lazy. Alright. So we would get this this one is equal to 2n times 2 equal to equal to c. Alright, equal to 2 power of n c. Right. When we use simple use with k equal to 1, okay, k equal to 1, where we can replace the n simply plug in with k equal to 1, we might say 1 times 2 equal to 2c. Okay, and then we would get, so that we will get c equal to 2 when k equal to 1. So this would be this answer, c equal to 2, k equal to 1, right? Because this one is cancel, and then c equal to 2, right? C equal to 2, and then k equal to 1. All right, so this is for the first function. Okay, let's have a look of the second function. Okay, okay, equal to 1. All right, so this is equal to 2 equal to c. When we use simple use with k equal to 1, okay, k equal to 1, where we can replace the n, simply plug in with k equal to 1, we might say 1 times 2 equal to 2c, okay, and then we would get, so that we will get c equal to 2 when k equal to 1. So this would be this answer, c equal to 2, k equal to 1, right? Because this one is cancel, and then c equal to 2, right? C equal to 2, and then k equal to 1. All right, so this is for the first function. Okay, let's have a look of the second function, where you have 2 to the power of 2n. Okay, let's check. We write it again, fx. Oops, you might want to use n here. Sorry, because we always use x, so it's confusing already somehow. Gn. And plug in the value of that, 2 to the power of 2n, because then we equal to c n here. And then if we see the pattern here on the left hand side, it should be less than or equal to 2 to the power of n. All right, since thus never outgrow the left hand side, can never ever. Thus, okay, thus we would say f n is not a big O of 2 power of n equal to 1. When you plug in n equal to 2, you might want to, and then you have this one here 16, and then c equal to 4, then so 4, c is equal to 4. So see, whenever n equal to 1, c should be equal to 1. Then n equal to 2, c should be equal to 4, and so on so forth. So this can be never be a constant value, all right? Not a value. So question number 9, and next we go to question number 10. Question 10, explain what it means for function to be big omega of 1. Big omega, so we call it big omega of 1. Okay, we know that big O, for big O notation, we have to prove fx less than c gx, where the fx is bounded above the c, okay, above the constant c. But for this big omega, another way around. So we need to prove fx should be larger than or equal to c gx. Okay. Then only we can say that this. When we can prove this, then only we can say that fx, the function fx, is the big omega of 1, or whatever function that is given to you lah. Now, how can we go like this? Whenever you can prove this, so that we can say fx is big omega of gx. So now that we've given fx larger than or equal to c1, okay, so this fx, modulus of fx larger than or equal to c1. So whenever x larger than k, so this fx should be equal to c. Alright, so c is this fx. So for conclusion, we can say that this function fx is bounded below the constant c with the interval of k and infinity. Okay, below constant c, this is the constant. So this is basically how you can explain what it means by a function to be a big omega of any function that is given there. Alright. Next, question number 11. Explain what it means for a function to be big theta by a function to be a big omega of big theta or k omega gx to be big theta of 1. Okay, now some recap. Okay, for big O notation, this one should be fx less than or equal to gx. Okay, number 1. Number 2, for big omega gx, okay, fx should be larger than or equal to gx. Oops, I forget to put the constant value. Sorry, constant value. For number 3, function to be big theta, it's supposed to fulfill the requirement of big O and also big omega, right? So means that fx should be equal to c gx here and larger than or equal to c gx here. So we may saying that this one is c1, this one is c2, while for k1 k1, this one is k1 and this one would be probably have k2. Okay, so this is for big theta. Okay, now how can we explain on the big theta? Right, as the given here, as the given the details on the number 3 here, we can just rewrite it again, where fx should be less than or equal to c gx and larger than or equal to c gx. Modulus of that. Okay. now we can say on the left hand side, for example, this one is C1 and K1. And here we can say that with C2 and K2, right? So most probably the maximum of K1 and K2, because you have two values of K and two values of C. Could be similar, it could be different. Okay. So this is for K, where K is the maximum of K1 and K2. All right. So basically, when you have shown this equation, so that's already fulfill the explanation of the function to be big data of the given function. And so not stop there, you can just saying fx is bounded below C1, okay, this one, below C1 and above C2. If you label here as C2, then it should be bounded below C2 and above C1. So it depends on the labeling that you do. So now on my screen, I label on the left hand side C1, which is this one is fulfill this big omega, and the right hand side fulfill this big O, right? So big O is bounded above the C, the constant C, while the left hand side, which is for big omega, it is bounded below the constant C with the given K1 and K2. So this is basically the explanations lah, more or less the explanations for question like this. Okay, just to show or prove that what is big omega and also big theta. Okay. Now we go to week 5 class activity. Very simple question, very simple things to do. You need to go through to CPT 112 eLearn portal under section week 4 WebEx recorded video. Now it's week 5, right? So go to week 4 section WebEx recorded video, and then you need to watch the pre-record video on induction and recursion under mathematical induction subsection, okay, subchapters. Start at the may this odd positive, then this is equal to n square. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. So this is the pre-record video for topic induction and recursion, chapter 5 from the main reference book. So chapter summary, we will only cover mathematical induction, recursive definitions, and recursive algorithms under this chapter. The exercise question. Rank of the ladder. Okay, imagine that we can reach the first rank of the ladder. So in this video, so giving the example of climbing an infinite ladder. Suppose that we have an infinite ladder. The first statement, we can reach the first rank of the ladder. Okay, imagine that we can reach the first rank of the ladder. Second statement, if we can reach a particular rank of the ladder, then we can reach the next rank. So from the first statement, we can reach the first rank. Okay, it is successfully, we can step on the step 1. So then by applying statement number 2, we can reach the second rank. And we apply the second statement again, then the third rank and so on. So we can apply second statement to any number of times to reach any particular rank, no matter how high up. Okay, so means that infinite number of the ladder step. So this example motivates proof by mathematical induction. So this is the principle of mathematical induction. So to prove that Pn is true for all positive integers n, we need to complete these basic steps. Okay, the first step is called basis step. Under basis step, we have to show the P1 is true. Then only we can move to inductive step, where you need to show that whenever Pk is true, then Pk plus 1 is also true for all positive integers k. Right? Because the principle of mathematical induction is to prove that Pn is true for all positive integers. So to complete the inductive step, assuming that we will get the inductive hypothesis that Pk holds for an arbitrary integer k. So that must be Pk plus 1 should be true as well. So referring back to the previous example, climbing an infinite ladder example. So basis step, by the first step, we can reach the first rank of the ladder, right? By the first statement, we can reach rank 1. The second one, inductive step, assuming the inductive hypothesis that we can reach rank k. Okay, the inductive hypothesis of this statement should be we can reach rank k. Then, by the statement number 2, we can reach rank k plus 1. Okay, by applying the statement number 2, k plus 1, then you may increase the number of steps of the ladder until you get the infinite integers. So hence, when Pk is true, then Pk plus 1 is also true for all positive integers k. Means that in this particular problem, we can reach every rank on the ladder. So important points about using mathematical induction. Maths induction can be expressed as the rule of inference. Okay, whenever you have P1 is the set with all integer k, when Pk is true, then Pk plus 1 is true for all n positive integer of Pn, where the domain is the set of positive integers. In a proof by maths induction, we don't assume that Pk is true for all positive integers actually. So we show that if we assume that Pk is true, then only Pk plus 1 must also be true. Okay. Proof by mathematical induction do not always start at the integer 1. So bear in mind, okay? So in such a case, the basis step begins at a starting point, okay? Whenever it's given in the questions lah. So usually we start with n equal to 1, but it not always start at the integer 1. Okay, now that this is the another example, to consider the domino standing. Consider an infinite sequence of dominoes which is labeled with 1, 2, 3, 4, 5, and so on. Let Pn be the proposition that the nth domino is knocked over. So we know that the first domino is knocked down. Okay, when the first domino is knocked down, which is P1, is true. So we assume that P1 knocked down, it is true. So we also know that if whenever the K domino is knocked over, it knocks over the K plus 1 domino. Okay, like for example here when P1 knocked down, so P2 will be knocked over as well. So it knocks over K plus 1 domino, means that whenever Pk is true, Pk plus 1 is also true for all positive integers. Okay, hence all dominoes are knocked over. It will simply follow until infinite number of domino. So Pn is true for all positive integers n. So now we would like to prove the summation formula by mathematical induction. Okay. So this is an example that shows that if n is a positive integer, then where's my pen? Then we would say 1 plus 2 plus something until n is the positive, the summation of this positive integer is equal to n plus 1 divided by 2. Okay, getting back of this equation. Okay, n plus 1 divided by 2. So the basis step is that, for basis step, P1, when you replace the n with 1, is true because why? Because 1 is always be true whenever 1 is the summation of the first integer, 1 plus 0 lah, because this is the first integer, right, in the list. So 1 replace n with 1, 1 plus 1 equal to 2. So left side is 1, and here is you substitute 1 for n. Okay, you replace n with 1, 1 plus 1, and then 1 plus 1 divided by 2, so equal to 1. So this is what we call it true. Now, okay. Now that we know whenever n equal to 1, the value is 1, n equal to 2, the value is 2, n equal to 3, the value is 3. So the summation would be 1 is 1 for the first one. For n equal to 2, the summation would be 2 plus 1 equal to 3, and then equal to 6, and so on. So this is the summation of the first positive integer. Okay, next what we will have. So this is just for you to review from the question. Now, we already have Pk is true, and we need to prove that Pk plus 1 is also true for all n positive integer. Okay. Now that we have Pk is equal to 1 plus 2 plus 3 plus something until you plus k. Okay, k integer. So this would be equal to k plus 1 equal to divided by 2. So this is what we call the inductive hypothesis. Okay. In other words, is that you are replacing the n with k. Okay, k plus 1 divided by 2. So whenever you replace the n with k, then you have the equation, right? So this would be inductive hypothesis. Just the simplest way to remember. Okay. Now that you already have this one, then when Pk plus 1 is equal to, this is k, right? So you are replacing k with k plus 1. So now we're replacing here k with k plus 1. K plus 1, k plus 1 plus 1. Okay, divided by 2. Then you simplify it with k plus 1, k plus 2 divided by 2. Got this? Okay, so this is the equation where you have for Pk plus 1. Okay, same goes to when you add left side and right hand side with k plus 1. to the left hand side. What is left hand side? It's for PK. Okay, PK. So this one is 1 plus 2 plus dot 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 plus K plus K plus 1. Okay. Same to this one is right hand side. So this is just to prove it true or not. Right hand side is the inductive hypothesis. K plus 1 divided by 2 plus K plus 1. Okay. You solve this. Solve everything. I'll try to help you with this. K plus 1 plus 2 K plus 1. Everything of this divided by 2. Then you solve until you would get same answer with this one. I don't have time and also space, so you can try it yourself. Try to solve this until you get K plus 1, K plus 2 divided by 2. So this is the proof of summation formula by mathematical induction. Now the second one, conjecturing and proving correct a summation. Try it yourself. Try to solve this until you get K plus 1, K plus 2 divided by 2. So this is the proof of summation formula by mathematical induction. Now the second one, conjecturing and proving correct a summation formula. Okay, just now is the first positive integer, right? So this one is the first and positive odd integers. How are we gonna do this? We try to list odd positive first, okay? Odd positive where n equal to 1 is 1, when n equal to 2 is 3, when n equal to 3 is 5, when n equal to 4 is 7, and so on. Okay, and so on until you have the summation. The summation for this. Now the second one, conjecturing and proving correct a summation formula. Okay, just now is the first positive integer, right? So this one is the first n positive odd integers. How are we gonna do this? We try to list odd positive first, okay? Odd positive where n equal to 1 is 1, when n equal to 2 is 3, when n equal to 3 is 5, when n equal to 4 is 7, and so on. Okay, and so on until you have the summation. The summation of odd positive. So the sum would be this one. This one is 4, 9, 16, and so on. Just like what we have here. Okay, because I just would like to rewrite it again in this way, it's easier for us to see and also identify the list. Okay, instead of writing like this list. So we can conjecture that the sum of the first n positive odd is n square. How? Let's see. This one. If let's say, see the pattern, n square. If let's say 1 square equal to 1, this one is equal to 2 square, this one is 9, 3 square, 4 square. So it could be n square for the summation of each of the odd positive integers here. Okay. So I'm gonna write this one. So this is the end of the list of the positive, the summation of the first n positive odd integer. So we may rewrite it like this. Plus 5 plus plus what should be here 2n minus 1 to stop. 1 equal to I'm sorry. Minus 1 and square. So this is the last value of the list where you get to n minus 1 to see the pattern here. To n minus 1 means that like for example, if n equal to 2, 2 times 2, 4 minus 1. 2 times 4 minus 1 is 3. 3 times 2, 6 minus 1, get 5. So this would be the formula of this odd positive. Then this is equal to n square. Hi.
No, this is good.
Hi, this is the second mathematical induction. Hi, this is the second video of subsection 5.1 mathematical induction. So we shall continue with conjecturing and proving correct summation formula. So in the previous video, we stopped here, right? So when we identify that pk is n square, right? pk is true when n square. Okay, now from here we can get the inductive hypothesis. The inductive hypothesis would be k power of 2, or we call it k square. So the inductive hypothesis would be k square when pk plus 1 is we say it's true. So we can simply replace k with k plus 1, where we can get k plus 1 square, and you might want to solve this one first. K plus 1, k plus 1, then you can solve it k square plus 2k plus 1. Okay, now you can see that, so this is inductive hypothesis, where you get it from when pk is true, right? When pk is true, then you can compose the inductive hypothesis with k square. This is for pk. So when pk plus 1, you'll get k square plus 2k plus 1. So see the pattern here, k square, k square. So this is the extra when you wanted to prove pk plus 1 is true. So what we're going to do with this equation, so we can add in the list, so that we can prove that this pk plus 1 is also true. Now, so the left hand side would be 1 plus 3 plus 5 plus 2k minus 1. Remember this one, so this is replaced by k, 2k minus 1 plus 2k plus 1. Plus 1. 2k plus 1. So this is actually the pk, then you plus this one. Okay. So this one. So this pk is inductive hypothesis. Its inductive hypothesis k. So this is k2 plus 2k plus 1 is actually square plus 2k plus 1 similar to k plus 1 square. Okay, so it's proof. It's basically you turn here and turn there, and then you will get this to in order to prove the statement. Okay, as long as you follow the steps on how to get the equation. Okay, to fulfill the question first, until you get the inductive hypothesis. First you settle. Okay, the step first, and then the inductive steps. Where here you might be using the inductive hypothesis. Then you prove. Okay, I would say the three main steps in order to prove the pk is true, then pk plus 1 is also true. Okay, that's for conjecturing and proving correct summation formula. Proving inequalities. Okay, use mathematical induction also seem to. Got this? Okay, so this is the equation where you have a plus 1 by 2. To prove that equalities, okay, so this is an example of inequalities. N less than 2 to the power of n for all positive integers n. Let Pn be the proposition, okay, that n less than 2 to the power of n. So now that you have n less than 2 to the power of n. So for inductive hypothesis, just replace n with k less than 2 power of k. So this is the inductive hypothesis of the statement. So when we wanted to prove pk plus 1 is also true, just now we already have pk is true, right? So pk plus 1 is also, we wanted to prove it is true. So when pk is true, okay, so this is pk. So because of this is inequalities problem, so we can have the from the inductive hypothesis, we have like k plus 1 less than 2 power of k plus 1, okay, plus 1 here and then here also plus 1, and this statement is less than or equal to 2 power of k plus 2 power of k. So this statement is equal to 2 times 2 power of k. This statement is equal to 2 power of 1 times 2 power of k whenever you have the same basic, okay, and this one is equal to 2 power of k plus 1 or 1 plus k also can. So here k plus 1, okay, whenever you have k plus 1, it's equal to 2 to the power of k plus 1. It is actually similar to whenever you have p k and also the inductive hypothesis k less than 2 to the power of k, right? You may also, it is also almost similar to when you plug in the value of k and replace with k plus 1. K plus 1. Okay. K plus 1 and then on the right hand side 2 to the power of k plus 1. But because of this is inequalities problem, you might need to settle like this, okay, before you can get it equal like this. All right. What else? So this is proving inequalities, settled. Next, proving divisibility. But because of this, k plus 1 and then on the right hand side 2 to the power of k plus 1. But because of this is inequalities problem, you might need to settle like this, okay, before you can get it equal like this. All right. What else? So this is proving inequalities, settled. Next, proving divisibility equal like this. All right. What else? So this is proving inequalities. Next, proving divisibility results. Divisibility results. Okay, what we have here. Okay, example, use maths induction to prove n cubed minus n is divisible by 3. Okay, can be divided by 3 for every positive integer n. Just use empty space here because it's only so we see there. I'll just use this screen. Now that you have, write it again. So basic step first. Basic step. When you replace n with 1 is true since 1 cube minus 1 is equal to 0. So this is divisible by 3. So it's always will be true. So this step is settled already. And then the second step, inductive step. For inductive step, you may need these inductive hypotheses first. How can you get this? By replacing the n with the k. So the k cube minus k is inductive hypothesis. So we may write this inductive hypothesis is similar to what? K cube minus k. K cube minus k. Alright. For k cube minus k, so this is actually, we get it from pk is true. When you want to plug in pk plus 1, okay, pk plus 1, so you just replace k with the value of k plus 1. K cube plus 1, so means that k plus 1 k plus 1 times k plus 1. Oops. Minus, so this is 2 minus k plus 1, isn't it? Okay, so you solve the equation first until you get this, you get this. So you settle on the left hand side first until you get, oh, this might be very, very long one. I suppose you can just continue by yourself. I'll just write down the settle. K cube plus 3k square plus 3k plus 1 minus k plus 1. Okay, so this one just rewrite again. Then from there, get k cube plus 3k square plus 2k, because this one cancel, and 3k minus k is equal to 2k. Then from this equation you simplify k cube minus k times this plus with 3k square plus 3k. So k cube minus k plus 3k square plus k. So this would be the first term, and this one we say it's second term. Okay, look at the first term. Is this divisible by 3? Yes, it is. Okay, when you replace the value, any value of k, it is divisible by 3, and the second term also divisible by 3. Okay, divisible by 3. See, So when the first term is divisible by 3, then this one is also divisible by 3. Okay? Therefore, n cubed minus n is divisible by 3 for every integer positive integer n. Okay, that's proving divisibility. Results. Okay, I think that's all. So this is the exercise which you need to solve to fulfill your class activity 1 of this week. Okay. So the question is, let Pn be the statement that 1 square plus 2 square plus n square equal to the statement n plus 1 to n plus 1 divided by 6 for positive integer n. Okay. So what's the statement of P1? Okay, so this is for basis step. Okay, show that P1 is true. Okay, that's proving by 3. Okay, the is cube plus 1. 1. Okay, so k cube minus k. Plus u square plus k. So this would be the first term, and this one we say it's second term. Okay, look at the first term. Is this divisible by 3? Yes, it is. Okay, when you replace the value, any value of k, it is divisible by 3, and the second term also divisible by 3. Okay, divisible by 3. See, so when the first term is divisible by 3, then this one is also divisible. Therefore, n cube minus n is divisible by equal to the inductive hypothesis. Monday, 9 of November. November 2020. Thank you very much. Assalamualaikum. And with the statement that 1 square plus 2 square plus anything plus n square equal to the statement n plus 1 to n plus 1 divided by 6 for positive integer n. Okay. So what's the statement of P1? Okay, so this is for basis step. Okay, show that P1 is true, completing the basis step of the proof. Okay. What so true is the inductive hypothesis? Remember, completing the four basis step. Okay, show that P1 is true, completing the basis step of the proof. Okay. What is the inductive hypothesis? Remember to replace the N with K. Inductive hypothesis. All right. Next, what do you need to prove in the inductive step? What do you need to prove? Yeah, I have already, let you know on every example before this. Complete inductive. Okay. So this is an example that show that if n is the plus one, not one. Okay, next. Then 4. Then you simplify it with k. Step, identify where you use the inductive hypothesis, then explain why this step show that this formula is true whenever n is a positive integer. Okay, so all the best. The link will be this one, and here is you substitute plus 1. Okay. You solve this, solve everything to get n, because I just would like to rewrite it again in this way. So instead of writing like this way, oops, of writing like this list. So we can conjecture that the sum of the first everything of this divided by 2. Then you solve until you would get same answer with this one. I don't have time and also space, so you can try it yourself.
Howdy, my name is Sabashalini and I'm here to explain how to represent a number in IEEE 754 32-bit floating point 63. So in this case it will be 131. The remainder is 1 divided by 2 again. It's 65. Remainder. This is the last step where you get a 0. Order. In this case, you start multiplying by 2 to the digit after the decimal point. So point 3, you multiply by 2, you get 0.6. Now, you have to keep track of the digit that precedes the decimal point in this column. So in this case, it's 0. So keep track of the 0. Now, take this over the next step, that's 0.6 times 2, and you get 1.2. Keep track of this digit, that is 1. Instead of doing 1.2 times 2 for the next step, you just take the digit that 2, keep track of this digit, that is 1. Instead of doing 1.2 times 2 for the next step, you just take the digit that follows the decimal point along with the decimal point. 0.4 times 2 0.2, and you can just would be gonna go back to that again, follow with the 0, then 0.4 times 2, you get 0.8. Keep track of this digit, that's 0. And then 0.8 times 2 gives you 1.6. Keep track of this digit, that's 1. So doing 1.6 times 2, it will be 0.6 times 2, and it will be 1.2. Keep track of this digit, 1. Now you can observe that this step is essentially this step. So you know after 0.6 you would again follow with these steps and then it would loop again. So instead of doing everything in writing, you can just assume it's gonna go back to that step, and so this column would be 0, 0, 1, 1, goes back again, so it'd be 0, 0, 1, 1, so forth. So 0.3 in binary representation would be 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, so forth. 1, 0, 0, so forth. You need to shift 8 times. So for each shift to the left, you need to multiply them. So the first step was
Okay, some additional explanation regarding the overlapping of the ones. Okay, so if you have groups that are, if you already have groups, okay, if you already have groups, and these groups are overlapping, all right, it depends how they overlap. Okay, it depends how they overlap. In the first example here, in the values, two the positive 0 multiply by 2 to the half can store the significant. Okay, bias. All right, so it's a bias representation. The floating point numbers are also normalized. Okay, what we see earlier, the numbers are actually normalized. Okay, it's normalized such that the leading bit, the most significant bit, which means the leftmost bit, will be 1. Okay, now since it is always 1, there's no need to store that number 1. Okay, so if you go back to this example, notice that it is 1.1010001. Okay, so it always starts with a 1. Okay, because we have normalized it such that it is, all right. So normally when we write decimal digits, we also try to normalize it to, let's say, 3 point something something something. Okay, and then we adjust the exponent accordingly. So if we want the exponent become smaller, then of course then we increase the value here. If you want the exponent bigger, then we reduce the value of the number. Okay, so that's how we balance the exponent and also the significant part. Okay, so normalization for binary floating point is, so negative floating point number, the exponent is 8 bits. Okay, with floating point. Okay, basically there are 4 phases. One is to check for zeros, because if either, so those are the important. Immediate formats for floating point. Now, what about arithmetic? Now, when you do arithmetic, again, there might be a possibility for overflow and underflow. And sometimes the overflow and underflow is caused by the exponent, and sometimes the overflow and underflow can be caused by the significand. Okay, just like exponent, sometimes we need to do addition, subtraction, then the exponent. Similarly, for multiplication and division, there are again a few steps. First, you check for zeros, because if it's a zero, then it will be a exponents. All right. For multiplication, activity 5. So just calculate the following floating point. So there's one addition problem and one multiplication exponents. Okay. And this is the try activity. Negative. Okay. What if the exponent is negative 20, but it's the same? Okay. What is the value 12? It as the simple format 8 1 2 5 multiplied by 2 to the power of 20. Now, how do you express that in binary? Okay, so if you look on the left side of your screen, then you can see 1.1010001, and that's the significant part. Okay, that's a significant part, times 2 to the power of an exponent. Okay, now the original value of the exponent is 20, remember? Okay, 20. But one format that we use to express binary floating point numbers is to use a bias notation for the exponent. Okay, a bias representation for the exponent. So when we want to express the value 20, we then add a bias to it. Okay, so in this case, if it's an 8-bit exponent, the bias value will
Okay, hi everybody. This is tutorial number 3. Okay, tutorial number 3 for Group A. The attendance is now on the screen. Please kindly take your attendance. You might want to take note of the password just in case some of your friends who are coming in late, you might want to help them in case some of them, ask for the password, so you can just put it on a chat box for them. Otherwise, I will show this again later after the tutorial has ended. And as usual, I think I'll give the announcements first. No particular announcement except that tomorrow will be our usual lecture. Tuesday at 2:00 in the afternoon, Malaysian time. Okay. Try not to miss tomorrow's lecture because I will also be releasing assignment 1 tomorrow. Okay, so important that you attend the lecture to get details of assignment 1. Okay, I shall now be breaking you guys into 2 groups again. Kang Sang will be taking 1 group, and then the balance will remain in this main group. Yeah, just give me a minute. I will break you guys into the breakout sessions. Okay, I think we have now all gone into our respective sessions. Just give me a minute. Okay. All right, so welcome again. This is tutorial 3, which we will cover some more questions on computer arithmetic, and also a couple of questions on digital logic, the simpler part. Okay, before we move into other more difficult digital logic questions, especially involving the other later topics. Okay, so let's move into the first question. Afiq, if you have just joined, yes, thanks Amir for sharing the attendance code. Thank you. You guys are very helpful. Very good. Okay, let's go into the first question. Okay, so first question. Express the following numbers in IEEE 32-bit floating point format. Okay, so it's negative 7.125 and also 1.65. All right, so if you recall, in the IEEE 32-bit floating point format, do you guys still remember the format? Can somebody just shout out in the chat box what is the format? How many bits for sign? How many bits for exponent? How many bits for significant? Can you guys just shout out in the chat box, please? One bit for sign, okay. 8-bit exponent, good. And Significant, significant, how many bits? 23 bits for significant or mantissa. Okay, right. So that's the format. Okay, 20 bit 23. Okay, so 1 sine 8 exponent, 23 significant. Okay, good. I think you guys got the idea. Okay, so let's look at negative 7.125. Okay, so the first step is actually to represent that into binary first. Okay, so can you all just shout out what is the equivalent in binary? So what is it in binary format? Okay. By the way, this one don't worry about the sign bit. So it's going to be negative. Okay, negative what? So how do you? So 7 will be at least 3 bits, right? And then you have point, another 3 bits. So 111.001. Yes. Okay. I think most of you got it right. So this is 111. So this is 7. Okay. This is a 7. And then 0.001. So this is 0.125. Okay, so I hope most of you got this part of the question correct lah. Okay, so yeah, so I'm gonna write it again. Negative 111.001. Okay, and this is basically times 2 to the power of 0, right? 2 to the power of 0 is 1. Okay, so it's times 1. So it's negative 111.001. Yeah, times 1. Okay, so how do we change this into IEEE 32-bit format? Remember, in the IEEE 32-bit format, you always start with 1 point something 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 something. Okay. So in this case, we have to move the decimal point 2 places to the left. And so that means we have to add 2 places to the exponent. Okay. So it's going to look 1.11001 times 2 to the power of 2. Did you all get that? Attendance password, please. Okay, I try not to get distracted, but yeah, somebody please help. Thank you so much. Okay, so negative 1.11001 will be times 2 to the power of 2. So yeah, this is almost the IEEE format, but remember, see the exponent. The exponent, this is the actual exponent, but for IEEE 32-bit floating point format, the exponent needs to be in bias representation, remember? Okay, so the exponent needs to be added with the bias. So 2 plus, what is the bias for 8 bits? 127. So in this case, you get 129. Okay, so the exponent, this is in decimal, of course. So the exponent in binary will be 1,000,000,1. Okay, so this is the binary equivalent of the bias exponent. Okay, so now we can represent it already lah. All right, so since it's a negative number, the sign bit will be 1. Okay, so this is a sign bit. Then we have the 8-bit exponent in bias representation. So it's 1,000,000,001. Okay, and after that, the 23-bit significant, right? The 23-bit significant, we only start from here. We don't have to start with the 1 point. Remember, that 1 point is always there, okay? And it's implied in the representation. So we start from this part onwards, okay? So it's going to be 11001, okay? And then on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so that's the representation in IEEE 32-bit floating point format. Okay, did everybody get that? Understand or not? So what if I convert 7? Wait, let me. What if I convert 7 to 0, 0, 1, 1, 1, and my exponent is 4. No, okay, okay, let me just get that on the screen. Huang Xing converted 7 to 0, 0, 1, 1, 1. Okay, then of course it's 0.001. Okay, but in this case, remember, IEEE floating format always starts with 1 point something. Okay, so you only move it 2 places. Don't move it 4 places, because if you move it 4 places, you're going to get 0.0111, then 001 times 2 to the power of 4. But this part is already wrong. Okay, that doesn't help you in the IEEE floating point format anymore, because IEEE 32-bit floating format always starts with 1 point something. Okay, so just remember, just move it 2 places, because after you move 2 places, you will get 1 point something. Okay, and therefore your exponent will always be 2 in this case. Cannot be 4 already. Don't move 4 places. You move 4 places, you're going to get 0 point something something something, which is not IEEE floating point format already. Okay, Kuan Sing? Okay, good. All right, let's go to the next question. Sorry, part B. Part B. Let me just remove the notation. Okay, so let's move to. Okay, let's move to part B. 1.65. Okay, 1.65. This is in decimal. Okay, now what is it in binary? Can somebody just shout out? One point 1010011, then 00110011. So in this case, you cannot represent the number exactly in binary. Okay, so you choose lah. You choose up to a certain point. When you get tired already, you stop. Okay, so don't yes, in some ways you can go until 23 bits, but yeah, after a while you can see a pattern already. Okay, so that means 0.65, you multiply by 2, you will get 1.3. Okay, and then that 0.3 you multiply by 2, you get 0.9, and then that 0.9 you multiply by 2, you get 1.8, and so on. So you collect this you collect these values, and as you're doing it, you will notice that you will repeat. Okay, you will repeat 0011 0011. So you will know a pattern already. Right? So this one will be converted to 1.101, then 0011 0011, and so on. So you decide on how long you want to stop now. Okay, so up to here, can and this is where's my pointer? Okay, this is times 2 to the power of 0. Can times 2 to the power of 0. And since this is already 1 point something something something, so we don't have to do any shifting of the significand anymore. Okay, so this will be the significand that we want to use. Exponent. We don't have to shift the exponent anymore. So the exponent is 0 plus the bias. Bias is 127. So your bias representation for the exponent will be 127. Okay, right. So let's do this in IEEE. The sign bit is positive, so it's a 0. Okay, and then the bias exponent is 127. 127 in binary is 0 1 1 1 1 1 1. So this is 127. Okay, and then the significand. Remember, we start from the numbers after the 1 point something. So this will be 1 0 1 0 0 1 1. Okay, how many already? 1 2 3 4 5 6 7 8 9 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so we stop here. All right. So did you guys get this? Can you understand? Can do or not? Yes, I think this is pretty simple. So just be careful. Represent it into binary, okay, and then shift the decimal point so that it becomes 1 point something. Adjust the exponent, okay. Then the exponent convert it to bias representation by adding 127, yeah, and then just show it in the IEEE format. So start with the sign, then the bias exponent, and then the significant. Anything that is after the decimal point, you just copy. Okay. Good. All right, let's go to the second question. Oh, this one is a handful. So the following number uses IEEE 32-bit floating point representation. So what is the equivalent decimal value? Okay. So this is already in floating point. So we want to get the decimal value. Okay. So what do you want to do first? What shall we do first? What is the thing that okay, in a 32-bit floating point format, everything is actually binary, okay, and everything actually has its own value, the same value, except which one? Is it the sign? Is it the exponent? Or is it the significant? Which one does not reflect the actual value? Well, a sign is the actual, where 1 is the negative, 0 is the positive, right? Exponent. Why exponent doesn't show the actual value? Because it's biased, correct? Okay, Theo, Theo. So the bias doesn't show the actual value. So we need to convert it to the actual value. Okay, so let's look at the A first. A, the exponent is the bias exponent. Sorry, the bias exponent is 100000111. Okay, and this is 135. Okay, 135. So you want to convert it to the normal exponent, okay, not bias exponent, but normal exponent. All right. So how do we convert this into the normal exponent value? What do we do to it? Minus 127. Yeah, very good. So this one, 135 minus 127, we're going to get our 8. Okay. The value of 8, decimal, of course. Okay. So now with this information, then we can start converting it into the actual representation. So the actual representation will be negative. Okay, negative because it starts with a 1. Okay, negative. And then remember in IEEE format, it always starts with 1 point something. Okay, 1 point something. And then the significant, we just copy lah. This is a significant, right? 101. Okay, and of course all the trailing zeros, no value because it's after the on the right side of the decimal point, so no value there. So this is times 2 to the power of what's the actual exponent? 8 lah. Okay, of course this is a decimal value lah. Okay, or strictly speaking, you should use 1000. Okay, yeah, okay, but the value is 8 lah. All right. So what is this? Can you convert to can you convert that to decimal? $416. Yes. Okay. So in the end, you will get something like if you work out 1.625, and this is times 256. Okay, because 2 to the power of 8 is 64, I think. Yeah. And then you will get negative 416. Okay, Azri, it's not 416, but negative 416. Okay, because it's a negative value. The sign bit is a 1. Okay. Yeah, but you get the idea lah. Okay. Okay, can everybody get this one? Can Okay. Then let's look at the B one. Let's look at B. B, the bias exponent is 0000111. Okay. this is in binary, so the actual value here is 15. All right. So 15 is the 15. We want to then convert it into the exponent, normal exponent value. So just now you are mentioning we minus 127. So 15 minus 127, we get negative what? Negative 112. Yeah. So negative 112 is the actual exponent value. All right. So this will be let's write out the value now. So it's a positive value because the sign bit there is 0. Okay, so it's a positive, and it's always 1 point something. Remember 1 point something. So 1 point what? 1 point this one. 1101. 1101 times 2 to the power of. So remember, when you do the exponent part, it's always 2 to the power of. Okay, 2 to the power of. In this case, it's negative 112 decimal. All right. And so what's the value in the end? Irfan, 1.8125 times 2 to the power of negative 112. Yes. Wait, okay, this is 1.8125. This is the decimal value of that, times 2 to the power of negative 112. Some more? Can you simplify that further? In decimal, so everything changed to decimal. Because the question wants what is the decimal value. So don't keep in 2 to the power of something anymore. Just let's change everything to decimal. Okay, we have another version, 3.49 times 10 to the power of negative. Okay, right. So this so after we have changed that 2 to the power of, we will get 3.449 something times 10 to the power of negative 34. Okay. All right. So yeah, all the answers are all right, no problem. But just make sure you change it into the correct the format that we want in the question. Okay. Hannah. Okay. I think you guys, appear to know what you're doing. That's very good. Okay. Okay. So we can move to question number 3. Question number 3 is a digital logic question. Okay. Okay, consider the following truth table. Okay, so the truth table you can see on the right. I hope you can see because yeah. Okay, so you can see the value of x and y, and then those are the inputs. Then you get the function. Okay, express it in sum of products and express the function f in sum of products and product of sum separately, and then simplify. Okay, so let's try the sum of products first. Okay, so sum of products, we collect the ones, correct? We collect the ones. But in the meantime, can some of you just can one of you just just share your solution, just share your screen and then just share your solution. I just want to take a look, see like any one of you have managed to work out the solution. Can somebody just share, please? Don't be shy. Can anybody just share your solution? Okay, never mind. Can somebody just share what is it in sum of products? Yeah. Just show it in sum of products. It means you collect the ones, right? And you collect the ones. Can you just show it? Okay, to show the not, just put the apostrophe sign. Use the apostrophe sign as the not. Okay. Okay. Some of you say not x, not y. or not x, y. Okay, that's correct. Okay, so we collect the ones. We collect the ones, meaning we collect these two lah. Okay, these two. So this will be not x and then not y. And then the next one is not x and then y. All right. What is your simplified solution? Okay, Sui already put the simplified version. The simplified version is x only. Okay, sorry, not x, not x only. So in order to get the answer for this one, we can bring out both the x's. Okay, and then we get not y or y. Okay, not y or y is always true, isn't it? True or not true, or not true or true is always true. Yeah. So in the end, you get not x. Okay. Can follow? All right. Okay. Then now we have product of sums. Product of sums, we collect the zeros. Okay. But in this case, it will be in the form of not f, right? Not f. So what is your not f? Can somebody just shout out in the chat box? What is your not f? Okay, when you express not f, it will still be in sum of products first. It will still be sum of products. Not. So it's x not y or x y. Okay, good. All right. So your not f will be x not y or x y. Okay, Chuan Yu. Yeah. Okay, same as Chuan Yu's. Okay, good. So this is not f. Okay. Can somebody just shout out the final answer right at the end after you have done your simplification? What do you get at the end? Okay, Sui has not x 1 plus y. I mean true or y. Okay. Sui, if you can still simplify your answer. Your not x bracket true or y. You can still simplify it further. Okay, because true or y is always true. So that will become what? Sui, true or y is always true. So in the end, your final answer will be not x. Okay. All right. Okay, let's do this. It's a little bit complicated. Why? Because this involves De Morgan's theorem a little bit. All right. So instead of not f, so now we become a normal f, and then we not the other side. And then after that, we can do De Morgan's theorem. Okay, De Morgan's theorem. That means we can then break this up. Okay. So then that becomes not x, not y, and not xy. Okay, I hope you all managed to get this one. Okay, and then this one, we can also break this up as well. So again, we do De Morgan's theorem. This will be not x, okay? And then this, instead of and, this one will become or, okay? Or not y, all right? So this is this one side, and then we have this side, not x. So instead of and, now it becomes or, okay, not y. Okay, so then we just clean up the inside, not x or y, and then this one is not x or not y. Okay, so that's after some cleaning. And then what we do now is we can then do this one multiply. Already not multiply lah. We end this one. Okay, so we do two separate ors lah, And then after that, this one and with this one. Okay, so let's expand it a little bit. Not x or y. Okay, and then we multiply with not x first. Okay, so that is on one side. And then or, and then on the other side is not x or y and not y. Okay, can? So then, where's my pointer? Okay, then now we do the individually we multiply. Okay, so then this becomes not x, okay, or y, not x, okay, or now we do the other side. Also do separately. I won't say multiply lah. We are supposed to end. I'm so used to the usual algebra. Sometimes it's confusing. Not x, not y, then or y, not y. Okay, so y not y is 0, always false. Okay, and then on this side, the remainder here, we can take x out. Sorry, take not x out. We take the not x out, and then we have 1. Okay, because x not x and not x is not x. So we want to keep the not x there. Okay, and then here is y, and then here is not y. Okay, now y or not y is always true. Okay, this is always true. This is also true. So in the end, you get not x true, which means it's not x. Okay, so that's one way of simplifying the product of sums. Now the product of sums actually comes here. Product of sums here. All right. So here is the product of sums. After you have converted the not f to f, then we will achieve product of sums where I show the arrow there. Okay. So that is product of sums. After that, we simplify it. After you simplify, it becomes not x also. So that means from that truth table, no matter how you want to simplify, you will in the end get up with not x. Even from the sum of products also. From the sum of product side, you simplify already, you get not x as well. Okay? Can follow? Can not? Yes. Thanks, Wee. Very good. I hope the others also can understand. Okay. Okay, let's move to question 4. Oops, sorry. Okay, question 4. Simplify the following expressions. Okay, let me get up my pen again. All right. Question A is ST plus VW or RST. Okay, can you guys just shout out what is your final answer? So let's write pointer or and y have and x ST or VW. ST or VW. ST or VW. Okay. Some of you got ST or VW. Let's compare. Okay. So this one we can bring out the ST. Okay, and this one you will get product of sums. Now the product of or R and then or VW. Okay, so true or R is always true. So this will be ST or VW. Cannot simplify any further, right? I don't see how we can simplify any further. Yeah. So Chuan Yu, Irfan, I think all of you got it right, Okay. So very good. Next one. So this is A. Let's look at B. B is A not B C or not A not B C or A B C. Okay, so what is your final answer for this one? Can somebody just shout out in the checkbox? Okay, we have some answer here. C, B, not B or A. Yes, not B or A. C, yeah, okay, very good. So far all your answers are correct. Aisha, Sinsian, who else there? Suyi, yeah. Okay, so let's try this, okay, before we start, actually one simple trick here is to, we add another A, not B, C. Okay. Now when we so that means we're repeating this one. This one is repeated. So A not BC or A not BC is still A not BC. So it's not affected by the duplication here. Not affected by the duplication. So let's see. We have not BC, not BC, not BC. So there are three not BCs there. So we can take out the not BC. All right, and we get A or not A. Not BC. Okay, we can keep this one. All right, and then we can do AC. Okay, like this one, AC, and then here also we have AC. All right, so we bring out the AC. Why? Because when we do this one, we get B or not B. All right, which will then help us in the simplification. Yeah. So this one, A or not A will always be true. So it's in the end we get not B, C, and then here we get, here also is always true. So here we get A, C. So from here we can bring out the C, and then we get not B or A. All right. So can you guys appreciate this one? Can? So the trick here is to make use of the duplication. When you have the duplication, then you can have additional variables to play around to see how you can group them so that you can simplify it. Yeah? Anna, so Jiawei, okay. Hope everybody else is okay. Okay, Ken, Good. So let's proceed to question number 5. Okay, question number 5. You are first asked you to list the truth table. Now this one is a little bit long lah. Let's just put it this way lah. Why? Because you're gonna have X, Y, Z. Okay, and it's going to be 0, 0. Then you have the F. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 1, 0, 1, 1. Did I miss something? Yeah, 0, 0, 1, 1, 1, 0, then 1, 1, 1. So there are 8 rows, okay, and then we need to find out the F. Okay, so in order to find out the F, the function is X not Y, Z, or not X not Y, Z, or X, Y, Z. Okay, so we have to fill in the value one by one. Okay, fill in the value one by one. So X is 0, not Y is, so look at this one, okay. So you're going to have X0, Y0, Z0. So X0, not Y is a 1, Z is a 0. Okay, then or 1, 1, 0 or 0, 0, 0. So this one is a 0 or 0 or 0. So and then this one is 0. So your F here is a 0. Okay, let me try the next one. We try the next one. This will be 0, 1, 1 or 1, 1, 1, okay, or 0, 0, 1. So this one will be a 0, this one will be a 1, and this one will be a 0. So in the end, when you OR them together, you will get a 1. So here the function will be 1. Okay, and so on and so on. You have to find out all the different 8 combinations to find out what are the F values. Okay, So in the end, for your A, I'll just simplify it for you lah. I'm sure many of you have tried it. Okay. Okay, those of you who have, okay, I think maybe I'll ask you all first lah. Can you give me the sequence? That means, okay, just now we have this discovered 0, 1 already, right? So can you please give me your answer? 0, 1, what else? What are your answers? 0, 1, 0, 0, 0, 1, 0. Thank you, Aisha. Okay, this is the correct answer. 0, 0, 0, 1, 0, 1. Okay. Thanks to Aisha, this is your truth table. Okay, your truth table will look like this. Okay, so that's part 1. Then after that, ask you to draw the logic diagram using the original Boolean expression. Okay, logic diagram. Let me just clear the screen first. So you all got the truth table. I'm going to erase it. Okay, so if you notice in the function, you have three terms, and then it's ORed. So what you need to do is, for the 3 AND terms, you need 3 AND gates. Okay, and all these 3 AND gates will go into one OR gate. Okay, and this will be your F. All right. So the first AND gate will have X, not Y, Z. So you have X, Y, and Z as your input. So the first one has X, okay, and then you have Y, right? You have Y, and then you also have not Y. Okay, so the Y goes in here, and then you have Z. Okay, so that's the first term. The second term is so this one counting already. Okay, let's look at the second one. Not X, not Y, Z. So not X. So you have this one here. So a bit complicated. Not X, and then not Y. So not Y. We can continue from this one. Not Y, and then Z. And continue like that. Okay, so then team this one already, and the last one is XYZ. XYZ. So we can borrow X from here. X, and then Y we can borrow there, and then Z. So can you guys appreciate this? Okay, like that. Did you all get something like this as well? This one? Did you all get something like this? Xinxian, okay, you got something like that. Yes, Yong Kwang also, okay. So you have to be a bit in. This is what I drew is not what you might get, because it depends on where you draw the line and then where you pull the line and all that. So that might look a little bit different, but essentially, yes, you need to have the 3 AND gates there, and then the output of the AND gate go into one OR gate. Okay, and then you decide how you want to feed in your inputs into the 3 AND gates. Okay, we count in this one also, and then that's done. Okay, can all right, let's go to part C. Okay, part C, I didn't check the question properly, and then I found out that this question is similar to question 4. Okay, so the Boolean algebra simplification, the answer is the same like question 4. Okay, same like question 4B, question 4B. So in the end, your question C should be the function will be Z0 this way, and not y. Okay, so that's C. The method is the same like question 4b. Right. So then we go straight into question D. Based on the simplified expression from C, draw the truth table again. So again, this one is going to be X, Y, and Z, and function F. So again, you draw your truth table 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And then your F. So your F now is okay to determine the first one. So this will be 0 and then 0 or 1. Okay, which will bring us to 0, right? So this one will be 0. Then the second one, so using the simplified version, so using the simplified answer, simplified function from C, then you try to find out. So this will be Z is 1, and then X is 1, X is 0, sorry, X is 0, and not Y is 1. Okay, so this one will result in a 1. Okay, so you get this one. So if you notice, where you go down, this question D will have the same answer like question B. Okay, so you're going to get 0, 1, 0, and then you have 0, 0, then 1, 0, 1. It'll be exactly the same like question B. Sorry, question A. What am I doing? Question A will be the same like question A. Okay, your truth table will look the same like question A. All right. And then the last one, based on the simplified expression from C again, draw the logic diagram. Okay, so the logic diagram will look something like this. So you have your OR gate again at the end, your function. And because you see the simplification is that you want to OR the X and Y. So you have X, okay, and then you have Y. You can not it already, okay, or not Y, okay, and then sorry, this is not F. Then this one I will put it into an AND gate. This will be F, and then this one will be Z. Okay, so and then compare. So when you compare this circuit diagram and you compare this circuit diagram, okay, so what can you conclude in terms of the number of gates? So from question B, how many gates? And from question E, how many gates? Can somebody just shout out? Question B. So question E has 2 gates. So E actually there's 3 gates because there's also one NOT gate there, right? So if you look at question E, you have one AND, one OR, and one NOT. So so question E actually has 3 gates. But what about question B? Question B, how many gates? Xin, you say 7 gates, or I can count only 6. Okay, Sui, my bad. Okay. All right. So the question B, yes, question B only 6 gates, and question E you have 3 gates. Okay. So that means through simplification we can economize in the number of gates, basically. Okay. All right. I think that concludes our tutorial today. Any questions? Okay, yeah, I draw one more NOT gate for the Z. Oh, okay. Yeah, not necessary because Z can just be used as it is. Yeah, you don't have to not the Z. Okay. Right. Any other details? Any other issues? Okay. If there's no other issues, thank you very much for joining today's tutorial. I will see you tomorrow afternoon for lecture. All right. Thanks. Bye-bye.